Hi class, I hope you're all doing well. So today we're going to continue our discussion of exoplanets. We're finally going to get to a discussion of all the exoplanets that we know of currently, the exoplanet catalog as we call it. So here in the first half of lecture, we're going to talk about all the methods that we've been using to discover exoplanets. We've kind of been setting ourselves up for that the last couple of lectures. So we'll talk about that here in the first part. And then in the second part, we'll take a look at the catalog. The size of it, the things that we've discovered, the missions that have really contributed to it and made it grow very quickly over the last many years. And we'll take a look at a couple of the more interesting systems that we've encountered in our searches. Okay, so in the background behind me is kind of an image like ones that we've looked around a lot this quarter, but I really put it up here to remind us that the things that we're looking for, the exoplanets themselves, have certain properties, and the things that are easy to see are the parent stars there. And when we've been talking about techniques, we've talked a little bit both about the properties of the star and how we can exploit our ability to observe the properties of the parent star. But as you'll see today, some of our techniques are dependent on the star itself, and some of our techniques are dependent on the properties of the planets themselves. And so we're going to talk about that push and pull. Some techniques are better than others in terms of their ease of use or their ability to be sensitive to planets of different sizes and different types. And all of them have their advantages and disadvantages in terms of telling us what the actual properties of an individual planet are. Okay, so let me go ahead and start a few slides. So we're going to talk about exoplanet search techniques today. And one of the things that all of the search techniques have going for them is the technique itself delivers on ways to measure the properties of the planet that we care about. The easiest properties are often the size or the mass and the orbital period, but as time goes on and our thinking gets deeper and our capabilities get better, we begin to imagine ways that we might be able to detect more exotic properties of the planets, like the existence of a moon, as you see here in the foreground, or the existence of rings around planets. We've not successfully done that yet with any planetary system, but if you hang out with planetary astronomers, these are the sorts of things they're starting to think about, because the technology is really getting exquisite compared to the way it was even just a decade ago. Okay, so literally the storyline today is I'm going to tell you 5 of the different techniques for detecting exoplanets. They are the 5 core methods. There are always other exotic methods that people are thinking about, but these are the primary ways and certainly the easiest ways given the technology we have that we've been using to look for exoplanets so far. So the first one you and I have talked about already, this is the so-called radial velocity method, where we're using the fact that the planet is tugging on the star and the star moves back and forth, and that motion produces a blue shift or a red shift in the light from the star. And we talked about that a little bit last class. And the important thing to remember about it, so as you can see here in this overhead view, as the planet goes around the star, it certainly makes the star move. But the only time we can detect that red shift or that blue shift is if the planetary system is tipped to us a little bit. So then the star, as it's being drug around by the planet, sometimes is moving directly towards us, or at least a part of its motion is directly towards us. That gives us the blue shift of the star right there. And then sometimes its motion is directly away from us, and that gives you the red shift of the star that you see during the other half of the orbit. If the star is viewed overhead, like you see right now in this part of the movie, then we don't ever see that blue shift and red shift. It has to be tipped just a little bit to our line of sight, and then we get that very definite shift in the spectrum of the light from the star. Now, the strength of that shift depends on the size of the planet, and how often the shift occurs depends on the distance the planet is away from the star. So we can get the mass of the planet and also its orbital period by watching for these Doppler shifts. Okay? Now, this view here shows you another aspect of this, which is the parent star is actually physically moving around. And we can certainly see that even if it's not moving around enough for us to detect the Doppler shift. So detecting the parent star moving around is usually called astrometric detection, or the wobble method. Okay, and so the idea here is that because the planet is pushing the star around a little bit, it wobbles in position. And so if you can accurately measure the position of the parent star, you can detect or infer the existence of a planet, making it wobble in place wherever it happens to be. So here you see what we're doing is we're measuring the wobble, the position of that parent star. But the way you do it is you measure its position in the sky relative to much distant stars that are farther away, and form a kind of fixed reference point for you to view the position of the star against. And so that's what actually gives you capability to do this. Now, there's other ways that the wobble method can be used, and that is for stars that are very close to the Earth. So stars that are very close to the Earth, they're moving in their own orbit around the Milky Way galaxy, and so they have what's called proper motion. They actually appear to be moving across the sky a little bit each year. And as the Earth goes around in its orbit, it produces this kind of loop-de-loop motion, because sometimes we're looking that way to see the star, and sometimes we're looking that way to see the star. And so you can see this kind of wobbling motion back and forth. But if you just account, as you see in the dotted line there, for the motion of the Earth producing the wobble, and then you actually measure the position of the star in the sky, you see sometimes it's not exactly where we expected it to be. Okay, and the explanation for that is it's wobbling in response to one of the planets or more of the planets in its planetary system, which cause it to shift back and forth. Okay, so this is also an implementation of the astrometric or the wobbling method. Okay. Now, one of the most exotic methods for looking for planets is something called microlensing. So those of you who know a little bit about astronomy may have heard of microlensing before. It's a technique that we've used for a long, long time to measure and look for dark matter. It's very well understood how it works. And basically the idea is that light can be bent in the trajectory that it passes, in the trajectory that it's traveling along, if it passes near a source of gravity. And so when it passes, say, near a star or near a black hole is the way we often describe it because it's more extreme, the gravity, if the photon's traveling in one direction, the gravity of the object, the black hole, pulls the light towards it. And so the light appears to bend around it. And that happens on every side. And it takes light that was originally going outward and focuses it down like a gigantic magnifying glass. So that's why it's called microlensing. So here's a very nice movie NASA made showing how microlensing works. You have some star, it's just sending its light out into the universe. It would normally go along those straight lines. But if some source of gravity passes between the star and the observer, it bends the pathways of those rays so that they cross, kind of like the light going through a magnifying glass does. So down there in the bottom, you see that light curve in the lower right. And that little blip there, I'll play the movie again. That little blip there is caused by the fact that if there's a planet around the star, when it passes between you and the distant source of light that you're looking at, the planet itself can produce a little bit of extra blip in the microlensing curve. And it's that little extra bit of blip that we're looking for that is evidence for the planet. Now, this technique has been used, but you can imagine the opportunity, the number of times that one star passes near enough in front of another star to produce this lensing effect is not, doesn't happen very often. And so it's not always the easiest method to use to search for planets, because those kinds of occurrences are rarer than other occurrences that we use to search for planets. Okay? Another method you and I talked about, we talked about this last time, is blotting out the star or occulting the star so that you can directly image the planet. If you can cover up the glare of the parent star, then the faint planet will show up. And then if you uncover the star, the brightness of the star overwhelms your view again, and then the planet disappears. Okay, and so this is a technique that requires you to be able to build an exquisitely accurate shade to put in your telescope that covers up the star in just precisely the right place in the precisely the right way so that you can see planets around the star. Okay, now that is a exquisite engineering feat, but it's been done successfully. Okay, so this is probably the most famous example. This is a star called HR 8799. It's about 129 light years away in the constellation Pegasus. And you can see in this image right there in the center, there's a yellow star that's printed. That's the center of the parent star. But you'll notice there's a black disk around it. And that black disk is an artificial blocking, what we call an occulting disk, that we put in the telescope to block the light of the star. And when we do that, you can see around that star there are 4 dots. There's one far away in the upper left. There's kind of one in the upper right. Down below the star, a little bit to the right, is another one, and very near the star on the line between those 2 on the right is the 4th one. Okay, now this was an image taken at the end of July in 2009, but what this group did is they went back year after year after year for I think the next 7 years and took this picture again. And what they showed is that those are actually planets because they can see them moving. Okay, so this was done with the Keck telescope. And they made a movie, which I'll play for you now, and you can actually see those exoplanets, those directly imaged exoplanets, orbiting around their parent star, the way we often imagine, or the way we sketch, or the way we make computer simulations of planets orbiting the sun. Okay, so this is probably one of my all-time favorite exoplanet graphic images because this is literally watching planets orbit their parent star. It's an exquisite bit of data. Okay? Okay. Now, this occulting, covering up the parent star, is something that we're artificially doing with our telescopes, okay? And we talked last time about the proposed HabEx mission, which is going to fly a gigantic star shade in space, and it'll be 100,000 kilometers away from the telescope, but it also will occult stars in the same way so that we can measure and directly image their planetary system. Well, nature naturally occults stars all the time, and some of you may have seen this. So in 2017, there was a total solar eclipse that was visible from the west coast all the way to the east coast of North America, and hopefully many of you got to see this. I was in Casper, Wyoming, and got to see it. It was exquisite. It was my first solar eclipse I had ever seen, but it was the sun being completely blotted out by the moon, a natural disk, passing between us and the sun, okay? Now, you and I happen to live in an exquisitely unique moment in time where the moon is just the right distance from the Earth such that it exactly and just barely covers up the sun so that we can have eclipses like this. Some of you may know the moon is slowly moving away from the Earth, and I forget how long from now, but hundreds of thousands of years from now, the moon will be too far away from the Earth. It's slowly receding from the Earth, and there will no longer be total solar eclipses like you and I see right now. Okay? Now, this happens on a much smaller scale, and some of you may have seen this. So in 2012, the planet Venus passed between us and the sun, and that big black dot you see there near the top is the shadow of Venus passing between us and the sun. The planet Mercury also passes between us and the sun. It's much smaller than Venus, so it makes a much smaller dot. Mercury does it, I think it's every 10 years or so. It goes in front of the sun twice, and so you have an opportunity to see Mercury transits, as we call them, all the time. This was the last Venus transit, I think, for the next 200 years or so. So if you didn't see this in 2012, you will not get to see it again. But as you might imagine, there's plenty of movies of this on the internet that you can certainly watch. But this gives you a sense of what is possible if you wanted to look for planets passing in front of stars. So this is probably the single most useful planetary detection technique that we've developed so far. It's called Planetary Transits, and it's exactly this here. We can measure the amount of light that we get from a distant star exquisitely accurately. And if a planet the size of Venus or Earth were to pass in front of the star, just like you see Venus doing here, we are capable today, we have the technology to measure the change in the brightness of the star, because Venus, or the planet around the distant star, is blocking part of the extreme brightness of the star. We're basically being shaded by Venus a little bit. It's like standing under a tree with one leaf. There's a little bit of blocking out of the sun, but not a lot. Okay? So this is the last method that we tend to talk about. It's called the transit method. And so what, I'll play this movie here. Let me explain what to watch for. So in the center, you see the planet orbiting the star. That's the thing we've been watching for this whole part of the lecture. But there in the lower left is the so-called light curve. So that is us measuring the brightness of the star. That's what's plotted on the vertical axis, versus time. Okay, so we just go back to the star and we measure the brightness over and over and over and over and over again. And so this will tip over so that the orbit is edge on. That's necessary so the planet can actually go in front of the star. And if you watch, when the planet goes in front of the star, you'll see that brightness that we get from the star dip down. Okay, so take a watch. Okay, so we're going to tip the solar system over here so that we can view it edge on, as is necessary for transits. So the planet, we can't see any light from the planet at this point, but as soon as it goes in front of the star, it blocks some of the light, and the amount of light that we see from the star dips. Okay, so we call that the transit. And based on how long that dip lasts, we can tell you how fast the planet's moving in its orbit. That's how we measure the orbit. And based on how much of the light it blocks from the star, how deep that transit is, okay, that big dip there, how deep it is, we can tell you how big the planet is. Okay, and so that's how we get the properties of the planet from this transiting technique. Now, the great thing about this technique is, more than any other of the techniques, this is the one that's capable of measuring Earth-sized worlds. All of the other techniques require the planets to be big or to have strong gravity. The wobble method and the Doppler method, those are really great for planets that are like the mass of Jupiter, okay? But once you get down to the Earth-sized planets, the effect they have on their parent star is really small. And so if you want to see Earth-sized planets, this is really the way to go. Now, the beauty of this is that it also works for multiple planet methods, okay? So here's a movie where we have multiple planets going around the star, and if you watch that light curve there, when a big planet goes in front of the parent star, you get a big dip, and the dip's pretty long if the planet's far away, okay, because it's going slower. And then when a smaller planet goes in front of the star, you get a dip, but a smaller dip. And if two planets happen to go in front of a star, then you get this stair-stepping dip, and the relative sizes of the dips tell you about the relative sizes of the individual planets. Okay, so this is why the transit technique has been so extraordinarily valuable. And as we'll discuss in the second part of the lecture, it's been very successful. There have been 2 missions, one called Kepler and one called TESS. TESS is flying right now, which have greatly expanded the overall number of exoplanets that we know about. Okay, so we'll talk about that for the second half of the lecture. That's all I'm going to say for this part about the transiting techniques. So let me know if you have any questions. I hope you're all doing well, and I'll talk to you again soon. Take care.